A universe this large carries an unsettling promise. No matter how far humanity extends its vision, there will always remain regions beyond reach. For centuries, astronomy has been driven by a simple hope, that if we keep building better instruments and looking deeper into space, the universe will eventually reveal its structure completely. We imagined that one day the cosmos would become a solved map, galaxies counted, origins understood, destiny predicted. But modern deep space observations are beginning to suggest something stranger. The farther we look, the more we discover that visibility itself may have limits built into reality. Recent deep field observations connected to studies of the distant universe have intensified a quiet tension inside cosmology. In some regions, astronomers find less detectable starlight than expected from earlier models. Not empty space, just less visible light than calculations once predicted should be arriving. This idea has sometimes been exaggerated into dramatic claims about unimaginable numbers of missing or disappearing stars, but the real mystery is more subtle and, in some ways, more profound. The stars may still exist. The galaxies may still exist. The question is whether their light still belongs to our observable future. In certain measurements, expected brightness appears reduced, ancient galaxies seem dimmer than anticipated, and the relationship between distance, expansion, and detectability becomes increasingly difficult to interpret. Suddenly the mystery is not about destruction. It is about access. We may be confronting the possibility that parts of the universe are not disappearing physically, but slipping outside the boundaries of what observation itself can recover. To understand why this matters, it helps to return to one of the most important discoveries in modern science. In the early 20th century, astronomers realized the universe is expanding. Galaxies are not flying outward through pre-existing emptiness. Rather, space itself is stretching and carrying galaxies apart. Edwin Hubble's observations revealed that distant galaxies generally appear to move away faster than nearby ones. Light crossing this expanding space becomes stretched into longer wavelengths, shifting toward red and eventually into infrared regions. For decades, scientists assumed gravity would gradually slow expansion. But observations of distant supernovae in the late 20th century revealed something unexpected. Expansion is accelerating. Something, still not fully understood, is overcoming gravity across enormous scales. That influence became known as dark energy. Current cosmological models suggest ordinary matter makes up only a small fraction of the total cosmic energy budget. Most of the universe appears dominated by invisible components, dark matter shaping structure and dark energy driving expansion. This creates a consequence that feels almost philosophical. There exists a distance beyond which future light will never reach us. Not because that light stops traveling, but because space expands too quickly between source and observer. This boundary is often described as a cosmic event horizon. Objects beyond it continue existing, evolving, and emitting light, but eventually their future signals become inaccessible from our location. Reality continues. Observation does not. Once that idea is extended across billions of years, the implications become difficult to ignore. Galaxies do not need to explode or vanish to disappear from our perspective. Expansion alone can isolate them. Imagine observing a distant city while the land between you stretches continuously. Even if the city remains unchanged, eventually the distance grows too rapidly for new information to arrive. The city still exists, but communication fails. Cosmology suggests something similar may happen across the universe. Light emitted long ago can still be reaching us today, while the galaxies producing that light have already moved into regions whose present state will never become observable again. In that sense, astronomy becomes an encounter with history rather than current reality. Deep observations are not showing us what distant galaxies are now. They show what those galaxies were when the light began traveling. As expansion accelerates, more regions become disconnected in observational terms. The visible universe is not fixed. It changes with time. Every year, some photons arrive for the first and last time. Every observation becomes a temporary opportunity. This changes how we think about cosmic maps. They are not complete inventories of existence. They are records of whatever information still reaches us. The farther away a structure lies, the less certain our access becomes. In extreme cases, entire populations of stars may contribute less detectable light than expected simply because expansion alters how that light reaches us across immense timescales. Inside this framework, the idea of missing starlight becomes less mysterious and more unsettling. The universe may not be losing stars, it may be losing visibility. Regions once connected to observation become increasingly isolated. Ancient galaxies remain embedded inside expanding space while their future light stretches, weakens, and drifts toward wavelengths that become harder to detect. Instruments improve and reveal more, but they cannot bypass the fundamental geometry of cosmic expansion. There are limits imposed not by technology but by the structure of spacetime itself. This creates a strange paradox. Humanity exists during a period when the universe remains unusually observable. Our night sky still contains information from across vast distances. We can measure background radiation left from early cosmic history. We can detect galaxies billions of light-years away. We can reconstruct earlier stages of structure formation. Yet this opportunity is temporary. If intelligent observers exist trillions of years in the future, their sky may look dramatically emptier. Local gravitational systems may remain, but distant galaxies could disappear beyond observable reach. Those future observers might struggle to reconstruct the true scale of cosmic history because evidence available to us today may no longer exist for them. In that sense, astronomy becomes an act of preservation. Every observation records information that may eventually become impossible to recover again. That realization transforms how we think about deep space exploration. Telescopes are not merely extending vision, they are collecting moments before they become unreachable. Every photon arriving from deep space survived an extraordinary journey through expansion, gravity, and time. Some began traveling before Earth existed. Others originated before the Sun formed. Ancient light crossing billions of years finally arrives at instruments built by a civilization that appeared only recently on cosmic scales. Yet instead of delivering certainty, these observations reveal a universe that remains partially inaccessible by design. The more the universe expands, the less of it can be observed from any one location. Growth creates separation. Scale creates isolation. The cosmos becomes simultaneously larger and less available. Whether discussions about missing light ultimately reflect evolving models, observational limits, or deeper cosmological effects, they point toward a truth that may be even more profound than disappearing stars. Reality does not guarantee visibility. Existence does not guarantee access. The universe is not a static backdrop waiting to be catalogued completely. It is dynamic, expanding, and constantly redefining the boundary between what can be known and what remains forever beyond reach. Somewhere beyond our observational horizon, galaxies continue forming stars, black holes continue shaping space, and light continues traveling. But some of that light may never arrive here. And perhaps that is one of the strangest discoveries modern cosmology has given us. Not that the universe hides things from us, but that distance and time themselves decide what parts of reality we are allowed to see.